Hello, my name is Kumar. I manage Essbase at Oracle. Today I'm going to talk about why Essbase. So what motivated me to talk about Essbase today is recently we celebrated 25th anniversary of the IPO of Arbor Soft, the company that created Essbase. Also recently met the two founders, Bob Earle and Jim Dorian, and they were very happy and proud that SBase is still going pretty strong and has got a lot of strong followers. Okay, so today I'm going to talk about the technical underpinning of SBase and the domain that it operates and so on. Okay, let me start sharing my screen. So Essbase is an analytic engine. Okay, it helps us to solve certain classes of analytical problems. So before we go into specifics of Essbase, let's look at the nature and the structure of the analytical problem. Okay, what I'm showing here is a denormalized table. Here, what we have is it shows the spend by year, quarter, month, purchase org and organization name, product and category, suppliers, and so on. So there are different business concepts like calendar, purchase org, product, and suppliers, and then the different types of metrics like spend, addressable spend, and so on. Okay, so when you have either a denormalized table or even a view or a collection of table joined together using a select query, the type of analytic query that you want to ask are like this, right? Typically, people are interested in, give me the spend by category, right? Here, if you look at this, this shows for this on the denormalized table, it shows the spend by various types of category, or you could do a spend by year. All of these are done through group by. So group by is very fundamental to most of the analytical operation. The reason is uh, typically the analytic users are not interested in the individual transactional row, but they are interested in more trend and group at higher level business concepts. So you want to group those transactions by certain business uh, uh, artifacts like or a grain as they speak, and all of these business concepts naturally form an hierarchy with higher levels of grain. The other type of query you can ask is in the same table, spend by suppliers or spend by purchase org, um, or you can even do by two concepts. Here it shows spend by category and year. Okay, where we do a group by two concepts, like year building in 2015 and 16 and so on. Okay, we can also do what is called a security sensitive aggregation, right? This becomes now more complicated. What we are saying here is, look, find all the join with the security table, like where the user is Kumar, and only all those spend that is associated with it. First, find them, and then group it by the product category. Okay, so and once you start imposing security, the complexity of the query keeps exploding, and I've seen queries which are like almost 80 pages of SQL. Okay, so this all of these are characterized as what we call as an aggregation. Okay, so most of these group by queries basically perform what is called an aggregation. So in the you can say it in a different way, right? So if you look at it, it is easy to prove that every one of the aggregation query is a point in this what we call as a multi-dimensional lattice or the tuple space. Okay, here what I'm drawing here is, let's assume in this there is a product, customer, and geography dimension. here they have three levels: level 0 of product, 1 of product, and 2 of product. Similarly, customer has 3 levels, and so on. What this node shows is Cartesian product of all the members of level 0 of product, level 0 of customer, and level 0 of geography, all of those points. And this one shows if I just group by or aggregate along product hierarchy from level 0 to level 1, this shows all the aggregates where we keep customer and geography at level 0 but product at level 1. And this one is grouping by geography, okay? And this one groups by product and geography, and you can so on. So this is why I'm saying, like, all those aggregation queries are some point in this multidimensional space, okay? So, and this shows the generic, so any analytic query is represented here, okay? And you can see, and it's also easy to prove that this size of this lattice is exponential, okay? Because we are multiplying, it's exponential in terms of the number of levels of the different dimension, okay? And once you, but the specific number of aggregates is exponential in the number of member combination, okay? So the question then is, to solve the aggregation in a general manner, we need to find an appropriate data structure that actually represents, that efficiently deal with this lattice. Let's say if we don't have a good data structure, and if we say, look, we are going to solve this just using a relational concept, then the problem becomes more like a consultant paradise, in the sense that this is how, so you may have 3 queries that may run well today, and then one fine day you will realize the queries are running slower. Then typically what happens is you will go and say you might have forgotten to update the statistics because you might have loaded some data that renders the previous query plan ineffective, or you may have to go create a new index, and so on. So it's a constant churn of tuning. I know there are many activities that have happened in the relational world, like columnar and in-memory aggregation and so on. But the fact that the rows and columns structure of the table do not represent the business hierarchy along which we do the aggregation makes it always a little inferior compared to a dedicated data structure that understands this tuple space of aggregates, okay? That's on the aggregation side. So what are the other types of problems that an analytic engine needs to deal with? So that the other side is what I call as a calculation, okay? So let's say, so what do typically analytic many users do? So for them, their preferred tool is Excel, okay? What they do is they download the data from either a transactional or a reporting or any other systems into an Excel, and they build Excel model, which is basically a calculation. So in the case of an Excel, what I'm showing here is some random set of calculation. Here you can see in Excel, you can drop precedents or dependent for every formula. Here, this is the formula. And you can see, and so this is another one, and so on, okay? So Excel provides you a 2-dimensional grid, which allows you to model any directed acyclic graph of formulas, right? You can have a formula of formulas and so on, and you can repeat it from in every one of the cells. So you can express very, very complex calculation that spans not only all the cells in this sheet, but you can have many, many sheets that refer to each other, okay? So it's very powerful in that sense, right? So basically, you may have a central server that does all the transaction, and you may even do an aggregation. Then you may download the data into Excel, and then you model all your calculation in Excel, right? So this is what typically people do, okay? And but because this Excel is so powerful, mean, do we need this complex capability where you can model any directed acyclic graph? Or not really, right? In my experience, I always keep looking for the patterns of calculation that are very common in various types of model. Okay, so here I keep looking for more and more patterns. So I classify some of them here. Okay, so if you look at the let's say first one is the ratio. I have profit, sales, and profit percentage metrics. This is the calendar dimension. So profit and sales are here, and then the profit percentage is computed at the month level like this. But the profit and sales add up. But if you look at profit percentage, this doesn't aggregate, right? So what you have to do is you need to compute profit percentage like this. Then you need to compute the aggregation of profit and sales. Then you need to compute profit percentage. So not all metrics behave the same way. So the calculation flow is something like this. So you need an analytic engine that allows you to express a flow like this. Similarly, if you go to unit price, this is another pattern where the price and units are loaded at a weekly level, and dollar is computed, dollar or revenue is computed at a leaf level, right? And if you look at the price is input at a weekly level, but it is computed at a monthly level, right? The arrows are reversed. So here what you have to do is you compute dollar at a weekly level, then you aggregate the unit, but the price is then it is derived. Okay, so this is in Excel where we model every formula as a cell by cell rather than a more compact representation. It's very important that any analytic engine which doesn't model cell by cell has an ability to model a flow like this. Okay, then another one is which is often what I see is what I call as a zigzag, right? So let's look at there is a beginning inventory of some product. Then this is the demand. This is how much I'm making, right? So the input inflow is inventory plus production plan. Outflow is demand. So the ending inventory is inflow minus outflow, right? So, but the beginning inventory of next week is the ending inventory of previous week, right? If you want to compute like this can have a very recursive depth of 52 weeks or 104 weeks. You need to be able to model calculation like this, right? So while aggregation points are aggregation queries are points in a tuple space, the calculation poses a different challenge where we should be able to model various types of calculation flow like this. So Excel is able to model because it's able to model any directed acyclic graph in this two-dimensional grid. But whereas if you're trying to come up with a data structure or an engine, you need to be able to model like Excel. But at the same time, the drawback of Excel is the size of the program is same as the size of the cell, right? If you have billion cells of formula, then the size of your program is billion, right? It's the size of the input. But whereas you may want to think of a more compact representation. The other type of pattern is what I call as an allocation. Like let's say here I'm loading the shipped unit here. The shipped percentage is ratio of my shipped unit to my parent one, right? So this you have to, the way you want to compute this is you load it here, aggregate to the parent, and then compute it here. That's a flow. Okay. And another one which is commonly seen is you compute forecast based on historical shift percentage. Here, what we are doing is, if you look at it, forecast is loaded at a higher grain so that you avoid some of the fluctuation at the individual SKU level. It's more loaded at a family level. But then if I want to compute a forecast at a SKU level, I look at the historical shift percentage, which is basically computed like we showed in the previous one, right? And then I take my parent forecast and I multiply it by the historical shift percentage with 1 year lag, right? So like this. So if so here shipped unit is aggregated, then shipped percentage is computed, the parent percentage is forecast is loaded, then my forecast is computed, and then I can aggregate it back, right? So it can get more complex by what I call as a consensus forecast, right? Here, this is how I computed my forecast. Then I can override it with a user override. Then consensus is, look, if the user didn't override it, take the computed one, otherwise take the user one. And this can be added, and this then can be used to compute, let's say, consensus forecast dollars, and like this flow can keep on going up, right? So what is it that is needed to do calculation like this? Okay, so there are many concepts that come into picture for an analytic engine to deal with it. Okay, the important one is solve order. Okay, here, for example, if you look at this, right, let's say I have a particularly when you don't express formulas, like for example, in the case of an Excel, the dependency analysis is very strong and very easy because everything is expressed cell by cell. It's very, you can imagine if you are given a structure like this, you can imagine how Excel, if you Excel engine can take cell by cell and compute transitive closure and some kind of a graph structure internally to compute this type of a flow, right? But we don't want to have a cell by cell formula. We want to have a dimensional model where you want to express the calculation in a more compact way, right? But let's say I may have a formula in only one dimension. Then when I am doing a Cartesian product with members from other dimension, then there is some amount of an ambiguity, and solve order comes to help in terms of breaking that ambiguity. Let me explain what I mean. Let's say there is a product one and price, and product one and units. Okay, so this one is along. So this dimension is along product. Okay, and this one is along the measure. Okay, so now unit and price need to be multiplied to compute revenue. Okay, then we sum it to get the product level revenue. There may be P1, P2, P3, and I'm not showing you P2, P3, and all of that, and so on. Or what we could be doing is we could be adding P1 and units and P1 price to similarly P2 price and P2 units to family level units and price, and you can multiply. So which one is right? Right? The engine doesn't know. If you just have a formula at a measured dimension, because it doesn't reflect how it needs to flow when I join with other dimension. So the engine may get confused. It doesn't know whether I should multiply first and then aggregate later, or aggregate first and then multiply, right? So this is where solve order comes into picture. If you put a solve order for revenue greater than the aggregation along product dimension, then the weighted sum would happen. But if you put the aggregation for unit greater than the solve order for revenue, then the aggregation will happen first and then the multiplication will happen. So that's because when you don't have a cell by cell calculation expressibility, if you have it at a dimension by dimension level, then the solve order is very, very important. So even if you have solve order, it is also very important to solve problems like this, where we go through many, many levels. You need to do what is called a dependency analysis. It's very, very critical that you can have like 30 or 50 levels of recursion, right? Where you keep exploding the formulas one by one. So we call that a dependency analysis, right? So a strong dependency analysis is very, very critical for an engine to have a very sophisticated calculation, right? So we talked about aggregation, which is basically a data structure that expresses captures the tuple space, and the calculation is captured by having a good solve order and a good dependency analysis. Okay, so what I'm happy to say is, so that's what is needed to define a good analytic engine. Okay, so So if I continue further, like if I quote Don Knuth, who's like kind of the god of computer science, he wrote, I come from I studied in the 80s where his books were so popular. He wrote several volumes about of computer programming. So he quotes like 95% of the problems in the world can be formulated as searching and sorting in computer science. So implicit in that statement is with appropriate data structure that achieves good asymptotic complexity for the algorithm as the input size grows, right? So aggregation and calculations are really critical for an analytic engine. So what's the appropriate data structure for these operations, right? That's the question at hand, right? So for anyone to claim that they are a good analytic engine, they really have to do a pretty good job of solving aggregation and calculation. And they need to have a good data structure that does this along various business hierarchies, right? So simply having rows and columns data structure as in a relational table is not good enough, okay? So, or it's not efficient enough to do sophisticated aggregation and calculation like security sensitive and whatnot, okay? The other thing I want to point out is um, when it comes to security sensitive aggregation, even security filters form a cube, okay, form a big tuple space. For example, we add this as a tuple space, right, for all of them. But if user one can only see certain geography, certain cost center, certain business unit, and user 15 can only solve some of them. Now what you have to do is this forms its own tuple space, and you need to intersect this tuple with the data tuple space, right? So it becomes pretty complicated. So if you have a clean abstraction that deals with both of these in a very purpose-built manner, then you will have a pretty good analytic engine. So I'm happy to say Essbase is such a data structure. Okay, Essbase is a purpose-built data structure for solving analytic problem. Okay, so I think I'm trying to be cute here. It's like if you're familiar with the early 90s presidential election, so you may understand this code. So it's a dependency analysis stupid, right? It's a very critical for an analytic engine to do a pretty good job in terms of the calculation as well as the aggregation, right? So so just restating whatever I said in that other Excel. Um, so Essbase is the best data structure to solve the analytical problem. Okay. So comparing and contrasting with the relational world, in relational rollup, we organize the access number using tables, views, rows, and columns, and so on. The operations are filters, outer join, inner join, and so on. You have to deal with update statistics, all of these issues. But whereas in the case of a multi-dimensional world or an analytic database like Essbase, we use language that is very close to what business users are familiar with, right? Dimensions, hierarchies, and so on. The kind of operations are very natural for business users, like aggregate, calculate, time balance, roll up, roll down, pivot, and so on, right? And it's also a purpose-built data structure that allows for very fast one of these, right? If you look at, if we go back to, if I go back to this data structure, Essbase deeply understands this hierarchy. If I pick a tuple from this node, it knows it has got a specialized data structures to know quickly find out who the descendants are, who I should aggregate to add up to this, right? This is encoded in our data structure, right? But whereas if you have rows and columns, that the concept of hierarchies or alternate hierarchies are not immediately available. So you need to build extra data structure. So the data structure is very critical. Okay. So so in terms of the various types of data management problem, Essbase is used in reporting analysis as well as what we call as the planning and planning write back and what if, right? So if you look at it, this tuple space need to be managed when the updates are constantly going on, right? It's not just you build the tuple space data structure one time, but you need to continue to manage that, okay? So just quickly go through some of the concepts. It can represent the multidimensional space very efficiently and can do various types of an aggregation. It models all the hierarchies in a first-class manner. It can also model what is called alternate hierarchies, meaning if you, let's say, have a fiscal calendar and a yearly calendar, you may have the January. If some companies have a different fiscal calendar, it may aggregate along hierarchies in a different way. Similarly, here we have a soda that it can add up to diet drink or as well as the normal soda. Okay, so it's a different ways of aggregating it, right? We do support that. Roll up and roll down are a very primitive and a fundamental operation that we can do very efficiently because there are data structures that represents the parent, child, descendants, and so on. Right? We are able to quickly find out who they are. And pivoting is again, like for a end user rendering, we can do it very quickly because we do understand these structures, right? All these are maintained in the phase of write back or a continuous data load happening at various levels of the queue, right? Particularly in Essbase, we have built-in financial intelligence that makes it very appealing to a lot of the finance users. Like we have a notion called expense reporting, variance and time balance and all of that, right? So time intelligence is another critical need. So basically these are all very primitive operations that are supported by the Essbase data structure, right? You can quickly find out year to date, quarter to date, month to date, and so on, right? And various types of calendars are supported. We not only support numerical values, but you can also support enumerated values for text and date. And similar to Excel, we can support a comprehensive list of functions, which performs various types of mathematical operations as well as the metadata operations along the business hierarchy. Okay, so typically the life cycle in an Essbase is you build the database, you load data, you calculate, or you can even aggregate up to certain level, then report, and then you can do nightly build, hourly build, or whatever cadence that you want to support. Okay, so there is a dedicated data structure. We call it an outline. It's basically the set of dimensions and hierarchies which we deeply understand, and we use this as a guidance to perform various type of operation. Unlike rows and columns, where you don't quickly know who my grandfather is, or here we can quickly find out who it is, and then that allows us to do the operation very efficiently, right? So we have what we call as a genealogy as a first-class data, part of the data structure, right? We have generations, levels, right? You can do a descendants of something, ancestor of something, siblings. These are all first-class operations. Okay, so let me stop here. In summary, Essbase is a great data structure for analytics. For analytics, if someone needs to build an engine, so they need to support aggregations and calculations very efficiently. And the way I represented the calculation, it's not a very trivial calculation. It involves you need to build strong dependency analysis to do the kind of calculation that the business users expect, like zigzag, allocations, aggregations followed by another allocation, and so on. Okay.